Good afternoon, everyone. Today we will move the discussion to the magnetic vector potential. But let us recap where we ended at last lecture. So we ended up last lecture by specifying or presenting the postulates of magnetostatics. So we said the curl. Let me start with the divergence. The divergence of the magnetic flux density is zero. The magnetic field does not have any point sources, and the curl of the magnetic field intensity is the electrical current density, right? So the magnetic field does have current sources, right? And the relationship between the flux density and the field intensity is related to constant mu h, and mu depends on the material or the medium, right? So those are the postulates. This is one and this is two. Two is called Ampere's law, very important law in magnetostatics. Okay, and then we contrasted this with postulates that we assumed or proposed for electrostatics, which are the following: divergence D, Gauss's law, equals rho v. Right, so this is Gauss's law. And then 2, which is the curl of E, the curl of the electric field intensity is 0, and the divergence of the electric field density, the electric flux density is rho v. Right, and D relates to E by the constant epsilon. Right, epsilon is the permittivity and mu is the permeability. They have different names, but they serve the same purpose. They relate the field intensity with the flux density. Okay, so this is 2. Now, in the case of electrostatics, we utilize this this axiom number 2, where the curl is 0 for E. We use that to state that, hey, E can be written as the divergence of some scalar field. And the scalar field we call the electrical potential. Right? If we assume that E has to be the divergence, sorry, not the divergence, the gradient. E has to be the gradient of some scalar field, right? Because the curl of any gradient is 0, right? Because the curl of E is 0, then it can be written. There is always a V we could find that if we take its gradient, we get E. Actually, if we take positive the gradient or negative the gradient, we will still get a good representation, a good enough representation of E, because it doesn't matter. It anyway turns to 0 when we find the curl of it, right? For historical reasons, we stick with the negative sign. Right? So, I mean, from purely mathematical argument, we could say that we could represent E as the gradient of some scalar field. It turns out we could interpret this field V as energy per unit charge, the voltage. That was the definition of the voltage. So we could interpret this scalar field as the energy it takes to move a charge around an electrostatic field, right? But that's an outcome of this definition. But really, I mean, the ultimate reason we could write E as the gradient of some scalar field V is because the curl is 0. We exploited this mathematical property of the curl being 0. Okay. Now, in the same manner, we want to exploit a similar property for magnetostatics to gain another field that we would call a magnetic potential field. In the case of magnetostatic, this field that we will call the potential field will turn out to be a vector field rather than just a pure scalar field. Why? Because the curl in the magnetostatic field is not zero, right? So we cannot write H as some gradient of some scalar field. This cannot be done because the curl of H is not zero. However, we could exploit the fact that the divergence of B is zero. How can we exploit that fact? Well, what kind of field, if we take divergence, we are sure to get zero? A curl field, right? If I have some field that's a curl field, if B equals the curl of some other field A, then divergence B, right, has to be zero, right? Because it's equal to divergence some field that's a curl field. We know that's this basic property, this one of the null identities of vector calculus, is that the divergence of a curl field is zero, right? So if we write B as a curl of some other field, we by default get the first postulates, because if we take the divergence of this, we will get zero. So this opens up now the definition of the magnetic vector potential. The magnetic vector potential is just another way of expressing B, just as V is another way of expressing the same field E. A is another way of expressing the same field, of representing the same field. It's all different representation of the same field. Just as the D is a representation of the electric field in terms of flux density, E is a representation of the electric field in terms of field intensity, right? V is a representation of the electric field in terms of scalar field, that if you take its gradient, you get E. Same thing, A is another representation of B, and A is defined as the thing that if you take its curl, you get B. And A, this A is what's called the magnetic vector potential. It's just another representation for B, for the magnetic field. You could either solve for B or H, or you could solve for A, and from A, after you found A, take its curl to find B. Right? Now there's now a big difference between the case of electrostatics, though, and the case of magnetostatics. In the case of electrostatics, the auxiliary field, the scalar that we defined, that we can solve for and then take its gradient to find the actual field, right? The auxiliary field turned out to be a scalar field, which is fine. But here, the auxiliary field that if we solve for, we can take its curl to find the magnetic field, turned out to be a vector field, right? And you remember when we discussed Helmholtz theorem, we said that to specify any field, any vector field completely, you need to define its divergence and its curl, right? Well, we know what the curl of A is. By definition, we said the curl of A is the magnetic flux density, right? Well, the question is then, what is the divergence of A? What should the divergence of A be? It turns out actually, and this is an interest, when the auxiliary field came out to be a vector field, it turns out this is not a straightforward answer to give. It turns out the divergence of A is a matter of choice. We could choose A to give us any divergence, but by choice, so we ensure that we make sure that whatever A we select, we select A such that the divergence of A is zero. This is by choice, right? Right? Why is it by choice, by the way? A could be anything, right? Let's say I find some A that if I take its curl, I get B, right? I want to show you why A could be that. I want to show you why we have freedom in picking A. right? We have some freedom in picking A because, hey, I found some A, I take its curl, I get V. What if I select now another A that's A plus the divergence of some scalar field? Not the divergence, I keep messing them up. What if I write A as A times the gradient of some scalar field? I just changed A in this manner. What if happens if I take the curl of the new field A, right? I still get B, right? Because I get now curl A plus curl, let me write this correctly, gradient phi, curl gradient phi. And we know what the curl of a gradient field is from, this is the other null identity. This is 0, right? So we still get B, curl A is B. So this tells me that I can take A and I can modify it. I have freedom to modify it and still get B when I take its curl, right? So A is not unique. That's what I'm trying to say. A is not unique, but we select A in such a way such that the A that we select has a divergence of 0. If you go deeper into the theory, this kind of property is called gauge symmetry. And it's a very important property in advanced electromagnetics, right? When we select the divergence to be 0, I believe this is called the Coulomb gauge, right? But it's, I mean, we won't go deep into that. We just have to know that for our purposes, A could be anything, but we fix A such that the divergence of A is 0, right? And we know what the curl of A is B, right? So this completely specifies A, knowing the curl and the divergence. Okay. What are the units of A, by the way? So I have curl A, right? I know what the units of B are. They are Weber per meter squared, right? What are the units of A? Well, we have to kind of go back to the definition of the curl. The curl is some has magnitude. I mean, it's a vector, of course, but let me actually do this. But the curl dot some unit vector in some direction, right? So this is the curl of the field, and I have some unit vector in some direction, right? The curl is going to be the limit. The curl dot this unit vector is going to be the limit of the contour integral over closed loop as delta S, which is the area inside this loop. This is C, goes to 0. So the curl is going to be, curl dot U is going to be the limit as delta S goes to 0. That's the definition of the curl, right? Of over the closed integral C dot dl over delta S. Okay, so this has no units, right? This is a identity vector, unit vector. Right? What about the units of this? So this has units of A times meter, right, over area, which is meter squared. So the curl has units, has the units of A over meter, right? Meter cancels with meter. And then B has units of Weber over meter squared. One of the meters cancels with this meter. So I end up with the unit of the vector potential, magnetic vector potential, being Weber per meter. Okay. Interesting analogy with the electrostatic case. In the electrostatic case, the units of V turned out to be volts. V, I mean, we defined it as V, right? And then E is just volt per meter. In the case of magnetostatics, the unit of the vector potential is Weber per meter, and to find B, we just take B, the units of B are related to the units of A by just taking the units of A and dividing it by meter. So we get Weber over meter squared. I always like to look at those analogies between the electric case and the magnetic case. Okay, so I mean, we haven't done anything fancy. All we've done is said, hey, instead of B, I can take some other vector A that carries all the information about the magnetic field. And how do I extract back the magnetic field from A? By just taking the curl. I didn't give you any physical interpretation of A, and it's, I think, useless to think about it because about a physical interpretation for A because it's just a mathematical construct. It's an auxiliary field that when you take its curl gives you back B. B has the real physical, clear physical meaning because, from the force law, B cross V times Q gives me the magnetic force from Lorentz law. Okay, so A is just an auxiliary field. Why even bother with proposing A? Well, I mean, there has to be some advantage to proposing A, and the advantage is that in some problems, it makes finding the magnetic field easier. Otherwise, if it makes things difficult, there's no point of it becomes just a mathematical curiosity. But it does make things simpler in a similar way that although it's still a vector field, it's not a scalar field like the electrical case, but it still makes things simpler, kind of like in the electrical case where the voltage is simpler to calculate than the electric field intensity. To find out how, we have to go back to the Biot-Savart law, right? So remember, the Biot-Savart law says that B, which equals curl A, right? Let's go back to the Biot-Savart law, right? What is H? H is I over 4 pi integral from point A to B. Let's say we have a current element, right? dl prime, this is the displacement along the wire filament, cross R minus R prime over R minus R prime cubed. Okay. Of course, I have B here instead of H, so I have to put mu here. All right, so I want to plug in, I want to find an expression of A. I want to modify this Biot-Savart law to get a direct expression for A from a current. How can, if I have a current filament, how can I calculate A instead of B? And I want to show you that calculating A for a current filament is simpler than calculating B. First, let's draw. Right, so I have the current filament. I have the displacement, small displacement, dl prime. Right, I have the point in space. Right, I have this is R prime. This is R, and this is R minus R prime. This is the setup, right? And this is the point in space where I'm interested in calculating the field. Right, so this is a graphical representation of the setup of the Biot-Savart law. Right? So I want to now show you like I want to do a calculation, and we did a similar calculation when we were studying polarization. So here we are repeating some argument that we used when we were deriving some stuff about polarization. And again, it's like a subtle argument, so pay attention. Let's take the scalar field that is just, so 1 over R minus R prime is a magnitude, it's a scalar field, right? So if I take the function 1 over R minus R prime, right, it's a It's a scalar field, right? The magnitude of this vector is a scalar, right? And it's a scalar field that varies depending on where P is, right? So it is a scalar field in space. If it's a scalar field in space, I can take its gradient, right? But to take its gradient, I need to assume a coordinate system. So I'm going to assume a coordinate system that is at the point of the displacement element. So I'm going to assume there is a coordinate system. I can assume any coordinate system I want. I'm going to use this coordinate system. This coordinate system that is at the point of the filament, right? And I'm trying to find the gradient of the scalar field, right, with respect to that coordinate system. With respect to that coordinate system, this scalar function is just, 1 over r, right? I'm assuming spherical coordinates, right? That's what it is. It's just a scalar field that represents the distance from that point of the displacement on the filament, right? What's the gradient of 1 over r? The gradient of the 1 over r as a scalar field is minus 1 over r squared, right? R hat. R hat is the unit vector in this coordinate system that I've placed on the filament, right? Whereas the theta hat and phi hat, they are all 0, right? Because the scalar function is only a function of r, right? All right. So what does that tell me? Let me rewrite this, and I can write that the gradient of 1 over r minus r prime magnitude, this is a scalar function, equals minus 1 over r squared. What's r squared? Let me write it back in the variables that have to do with the Biot-Savart law. R squared is just r minus r prime magnitude squared, right? R minus r prime magnitude squared. What's r hat? R hat is written in terms of this blue coordinate, right? But what is it? It's always pointing in terms of the blue coordinate, it's always pointing in this direction. This is r hat of the blue coordinate system. Okay, it's always pointing in the same direction as r minus r prime, right? So r hat in the blue coordinate system is always going to be equal to r minus r prime. It will be in the same direction of r minus r prime, but we need to turn that into a unit vector. So I put in r minus r prime over another magnitude, right? I want to turn this into a unit vector to get r hat. So this becomes r cubed. So this gives me this relationship. It's a subtle argument, so if you don't get it from the first time, that's fine. Go back and think about it. But we can write the gradient of the scalar function as minus r hat over r minus r hat magnitude cubed. This now, the right-hand side exists inside the Biot-Savart law, right? I have r minus r hat over r minus r prime over r minus r prime magnitude cubed. Right? So let me rewrite the Biot-Savart law then. So B equals curl A equals, using this fact. So it's going to be integral dl prime ui over 4 pi integral a to b dl prime times, there's a minus sign here, right? So I have to put a minus and take a minus in. So I put a minus out here and put a minus in so that I can rewrite the r minus r prime over r minus r prime magnitude cubed as a gradient of this scalar field. Right? Okay, so what comes next? Well, now comes, again, I told you this is very similar to what we did for the example of polarization. Now comes the application of the Leibniz rule for curl. So there's Leibniz rule for one-dimensional differentiation on the real line, which is the product rule. There's the Leibniz rule for the divergence of a scalar field times a vector field. There's also the Leibniz rule for the curl of a scalar field times a vector field f. I'm going to write it in general. So the curl of phi times f is going to be phi times the curl of f plus divergence of phi cross product f. Okay, so this tells me I can take this expression, divergence, sorry, not divergence, what I was trying to do. Okay, let's take this curl. Let's say I take the curl of dl vector. Oh, this is a vector, by the way. Let me see if I put a vector up there. Yeah. Over r minus r prime. Right? Let's say I'm trying to take the curl of this. So I end up, and let me apply the Leibniz rule to this. Right? I just want to show you that we get something that we can substitute back into that integral. So this is going to be the scalar field 1 over r minus r prime magnitude times the curl of the vector field, curl dl prime, right? Plus the curl of the scalar field, which is curl, sorry, the divergence of the scalar field, which is divergence of 1 over r magnitude minus r prime magnitude, right, times dl prime vector. Now this is the curl of dl. What is dl? dl is the displacement vector along the wire, right? It's clear that this vector is just a displacement vector. It goes around the loop of the wire. It does not have a curl. It does not rotate. And in any way, it's not a vector that's distributed along all of space. It just exists in the line, right? So it's clear that its curl is 0. This is 0. So we end up with this thing, which is the same as what we have inside the integral, being equal to this thing, right? So I can go back. Oh, I have one complication. Here I have the gradient times cross the dl. Here I have dl cross the gradient, right? Well, the solution is just to take the minus back in and swap the two terms. So remember we said a cross b minus equals b cross a, right? If you swap the term, you multiply by minus 1. So here what I can do, I can swap the terms and then just get rid of this minus sign, and I end up with this expression, the same as this expression, which I can substitute for it this expression here. So I end up with b equals curl a, we're almost there, equals mu I over 4 pi. I got rid of the minus sign just to swap the cross product, to switch the cross product here. And instead of this gradient cross dl, I end up with this term here. I end up with curl, because this equals that, right? So I end up with curl dl, this is prime by the way, prime over magnitude r minus r prime. Okay, the curl is linear. Because the curl is linear, I can take the integral anything outside inside the curl. So I can rewrite this as b equals curl a equals the integral from a to be, oh, I took the anything outside, I go along with the integral inside the curl. So this equals curl mu I over 4 pi. This is due to the linearity of the curl, right? dl prime over r minus r prime magnitude, right? If you have something linear and you have a sum, you can take the sum inside. So this is equals curl sum A, right? And an integral is just an infinite sum. It's just an sum with infinite number of components, right? All right, now we have a direct correspondence. And we can say that A then equals mu I over 4 pi A to B d, oh, let's forget the vector, dl prime over r minus r prime magnitude, okay, Weber per meter. And this is the expression of the Biot-Savart law in terms of A, in terms of the vector potential. And this seems like a much easier law to use, right? Because a much easier representation of the law to use. Why? Because first, you remember when we calculated using Coulomb's law and we had the cubed and the denominator, and then we went to the vector representation and we didn't have the cubed anymore. We have power 1. Same thing here. We don't have r minus r prime cubed. We have r minus r prime to the power 1. And then we don't have the cross product anymore. We don't have to worry about the cross product anymore. We can just simply use this law. In many problems, it's easier to calculate A. Then after you find A, you just take the curl of A to get B. But yeah, this is a much simpler representation of the Biot-Savart law with an intermediate step, which is where you have to calculate the magnetic vector potential first, A, and then after you calculate A, you take its curl to find B. The interesting thing about A, notice that A will have the same direction as dl, as the same direction as the current element. So if I have some dl prime with the current passing through it, I, right, then the A vector dA, well, I mean, the whole A vector is going to depend on the whole current, right? dA is going to be in the same direction as dl. So A kind of like looks like sort behaves as if it's current-like in space. It kind of parallels the current. So if you have the current going through a filament, the A vector will always be parallel. So this is I. The A vector will always be parallel in space to the current filament. So this is what the A vector in space will look like. And then the B vector will be both, and this is, by the way, dl prime. B vector will be both perpendicular to dl prime, both perpendicular to the filament and perpendicular to A, right? So B would be pointing out of the page, perpendicular to both the current filament and the filaments of A. So this also makes A easier to visualize. It always runs in parallel with the current. Okay, it's a mathematical construct that's very useful and that makes solving a lot of magnetostatic problems easier. So what we have done so far is we started with the Biot-Savart law, and we reached an expression for A. An important question is that the big assumption here is that the Biot-Savart law is an earlier experimental law for expressing the B field and the H field, empirical law, and another empirical law that we used as the foundation for the postulates of magnetostatic is Ampere's law, and we said those laws are equivalent, right? If those laws are equivalent, starting from law 1 or law 2, we should arrive at the same A, right? So I want to next prove that we do arrive at the same A, and I want to use this to prove to you that the Biot-Savart law and Ampere's law are equivalent laws when it comes to finding the magnetic field, right? Because they generate the same A vector, and we know that the B field is just the curl of A. So if regardless of where we start, we get to the same A vector, that means the two laws are equivalent. Okay, so we started with the Biot-Savart law and we got an expression for A. I want to now start with the Ampere law and get an expression for A and show you that the two expressions for A are equivalent. And this will verify the equivalency between the Biot-Savart law and Ampere's law. So let's start with Ampere's law. What does Ampere's law state? It states that in its differential form, it states that the curl of the magnetic field intensity is the current density, right? And I can write it, I can multiply both right-hand side and left-hand side by mu naught. Let me assume vacuum, right? So I can get the curl of B equals mu naught J, okay? Now, we said that B can be written as the curl of A. So I can express this as the curl of A equals mu naught J. Now this is a second order curl, and it arises in the expression, as if we remember from vector calculus, this arises from the expression of the vector Laplacian. Right, so nabla square A is the vector Laplacian, and it's defined as a combination of two second order vector differentiation operators. The first one is the divergence of A. It's the gradient of the divergence of A. That's a second order operator minus the double curl. Okay, so the double curl shows up in the definition, the expression, which I took as a definition of the vector. I presented to you as a definition of the vector vector Laplacian. This is called the vector Laplacian, in contrast with the scalar Laplacian, which is what? Which is divergence, no, sorry, gradient U, divergence. So it's the divergence of the gradient of the scalar field U. Right, so this is the scalar Laplacian. Okay, so I can take this and plug it in back into this equation, right? So this is equal to, this is clearly equal from this expression, this is clearly equal to the gradient of the divergence of A minus the vector Laplacian of A equals mu naught J. And we said we have what's called gauge symmetry in expressing A, meaning we can tune A, select A such that its divergence is 0. And this is where we apply it here. So we want to make sure that this is 0. Right? So A is selected in a way such that this is 0. This allows us to simplify the expression as the vector Laplacian of A being equal to minus mu naught J. Okay, where in this case, because the divergence of A is 0, the vector Laplacian of A is going to just be minus the double curl. That's the definition of the vector Laplacian in this case. It's just minus the double curl because in this case the divergence of A was selected to be 0 by choice. Okay, so this is a vector expression. We can kind of like try to look at the scalar we can apply this operator to A and check the scale, compare the scalar components of the right hand side with the scalar components of the left hand side. And to do this vector Laplacian, really all we need to do is the double curl. Right, so let's remind ourselves of what the curl is in Cartesian coordinates. Remember, we have to select coordinate system first before we can calculate the divergence or curl or gradient. So what is it in Cartesian coordinates? Well, I can write it down. So the x hat, and I don't have to memorize it. So I know the x hat component starts with, so remember that circle, x, y, x, after x comes y, after y comes z, and then z goes back to x. So the x component has a delta y here minus something over delta y minus something over delta z. I'm just writing down the pattern. And then here I take the cross, right? So this becomes az, and this needs to be ay. So the pattern is easy to memorize, right? To figure out without memorization. And then the y hat component is going to be delta over delta. After y comes z, and then after z comes x. So this is going to be ax, and then this is going to be az. And then the z hat component, so it's going to be delta over what after z, what does come after z? X, right? Minus delta over delta y, because y comes after x, and then I have here ay, and then here ax. All right, so this is one curl. What's the double curl? The double curl is just, you know, the repetition of this, right? So I repeat this same process. Or let me do it this way, right? I'll repeat this same process again. Yeah, the same process. I'm gonna repeat it again, but now my ax component, ay and az components are those components. Okay, so what is now the, let's just do the x component, right? It will be the same for the rest of the components. So for the x hat component, what do we need to get? Do we need to get first the az component? What's the az component of the first curl? It's going to be delta ay over delta x minus delta ax over delta y, and then we need to differentiate it again by y. So this becomes delta squared delta x delta y delta squared delta y squared. See what I did? I repeated the definition of the curl twice. Okay, then I need to take minus the second term here, which is delta ay over delta z. Well, what's ay? Ay is delta ax over delta z minus delta az over delta x. That's what ay is, and then I need to differentiate it again by z. So I end up with delta square ax over delta. Is that correct? Yeah, that's ay. So it's going to be delta square ax over delta z squared, right? And then delta squared az over delta x delta z. Okay, so and then I take the minus n, so this is equal delta squared ay over delta x delta y minus delta squared ax over delta y squared minus delta squared ax over delta z squared plus delta squared az over delta x delta z x hat, right? And then I don't want to do the y hat components and the z hat components. I want to show they're going to have, from symmetry, they're going to look the same as the x hat component, right? But what is this? Right? I want to simplify this. Remember that we said we selected the divergence of A such that it becomes 0, right? What is the divergence of A in Cartesian coordinates? It's delta AX over delta X plus delta AY over delta Y plus delta AZ over delta Z. That's the definition of the expression for the divergence in Cartesian coordinates, right, for a vector A. We said this needs to be equal to 0. Okay, so that's fine. Let me now take this and differentiate it again by x, right? So 0 differentiated by x remains 0, right? So I end up with delta a x delta squared over delta delta squared ax over delta x squared plus delta squared ay over d delta x delta y plus delta squared az over delta z delta x equals 0. All right. Notice those two expressions. This is this term, and then this is this term, right? So those two terms are just equal to minus delta squared ax over delta x squared, right? So instead of those two terms, you see that I can substitute from the expression, the equation that I get from the divergence of A being 0, I can substitute instead of those two terms minus delta squared ax over delta x squared. So that tells me that the double curl, the x component of the double curl, yep, ignore the y component for now and the z hat component, the x component. So instead of those two terms, I have minus delta squared ax over delta x squared, and then I have the other two terms, which are minus delta squared ay over delta y squared, sorry, ax, right, minus delta squared ax over delta z squared. Okay, and I would expect from symmetry that the y hat and the z hat components will look the same. The only thing is that instead of ax, I'll have ay, and for z hat, I'll have az. So take the minus to the other side. If I take the minus to the other side, I end up with the vector Laplacian, right? That's what the definition of the vector Laplacian is. And it turns out, the vector Laplacian, sorry. So I take the minus to the other side, I get minus double curl, which is, in the case of the divergence of A being 0, gives me the vector Laplacian of A equals the scalar Laplacian. So what is delta squared over delta x squared, delta squared over delta y squared, delta squared over delta z squared? It's the scalar Laplacian. It's the Laplacian of a scalar function, ax, equals the gradient of ax divergence it's the divergence of the gradient of ax. So it's the scalar Laplacian of ax, x hat, plus the scalar Laplacian of ay, which is also called the Laplace, just called the Laplacian. Typically, we call the scalar Laplacian just the Laplacian, and the vector Laplacian, we just add the word vector, right? It's going to be delta squared ay y plus delta squared az z. Right? So going back to this equation, right? I know that this as a vector, its components are the Laplacians of the. So we have the Laplacian of ax x hat plus the Laplacian of ay y hat plus the Laplacian of az z hat. So comparing components on the right hand side and the left hand side, we get those equations that we need to solve for to find the x component and y component and z component of a. The Laplacian of ax, so taking just the x component of a as a scalar field and finding its Laplacian, it should be equal minus mu naught jx, the x component of the current density. Laplacian of ay equals minus mu naught jy, and then Laplacian of az equals minus mu naught jz. Why do I want to express ax and ay and az in this form? Because I want to use the result from electrostatics. In electrostatics, and I mean, we didn't go through this actually because this is part of chapter 5, and this is a chapter we omitted. But I'll give you the highlight briefly. Right? The highlight is this. I start with the divergence of E equals rho over epsilon naught. I write, instead of E, I write E as the gradient of some vector field, scalar field V, the vector potential. Sorry, the electric field potential. So that's going to be rho over epsilon naught, right? I take the minus sign to the other side, I get divergence of a gradient of V equals minus rho over epsilon naught, and I said this is the definition of the Laplacian. So this is Laplacian V equals minus rho over epsilon naught. This is called Poisson's equation. French scientist. Right? Poisson's equation. And we know how to solve this. Even if I didn't discuss it with you or give you the solution, we know how to solve this because we know how to express the solution of this is the voltage that applies to this charge distribution. And we know how to calculate the voltage for any charge distribution, right? So we naturally know what the solution of the Poisson equation is. The voltage at any point in space, so if R vector is points to any point in space, is just from Coulomb's law, right, is 1 over 4 pi epsilon naught, and then we integrate over the volume. What do we integrate? Let me write this here actually, giving myself more space. Okay, so we know how to find the voltage for any charge density, volume charge density. Right, so we know that the voltage at any point, this is the position vector to any point, is just 1 over 4 pi epsilon naught, the volume integral, over what? Over this, the whole charge density, rho r, right, dv prime over r minus r prime, right? So this is the charge distribution rho, and then r prime points to a point in the charge distribution, right? And this is p, magnitude. So this is the expression of V. So even without knowing it, you know how to solve the Poisson equation, because for any charge distribution, you can calculate the voltage using this equation that we discussed when we were talking about when we were doing chapter 4. Right? And this turns out to be a solution for the Poisson equation. The point is that those are 3 different Poisson equations that should have a similar solution to the expression for the voltage. Right? So that means that I can easily now solve for ax at any point in space pointed to by r as being, right? Now the difference is, of course, instead of 1 over epsilon, we have mu naught. So wherever we see, oh, and instead of minus 1 over epsilon, we have minus mu naught. So wherever we see minus 1 over epsilon, we just substitute, wherever we see 1 over epsilon, we substitute mu naught, right? So here, instead of 1 over epsilon, I have mu naught over 4 pi. Where does the minus sign go? Well, the minus sign is still there, right? But right, yeah, which is fine because the Poisson equation has the minus sign. So forget the minus sign. Even with the minus sign, the solution is going to be this. Okay, I got confused a bit about the minus sign, but this is exactly similar to those three Poisson equations. And we have a minus sign, and we have a source. Instead of rho, we have j. J is like the kind of like the components of J are kind of like the new densities distributions. And then the minus sign is there. And then instead of, the only difference is that instead of 1 over epsilon, we have mu. So instead of 1 over epsilon, I put in mu, and then this is the solution. I have to integrate over v prime, jx over r prime over the source. Oh, my mistake here is that I didn't put r prime. This should be r prime. Okay, dv prime over r minus r prime magnitude, right? And then this is now a y r, which is equal to u naught over 4 pi. I'm just repeating the same thing. V prime j y r prime dv prime over r minus r prime magnitude. And then a y r equals mu naught over 4 pi. Same thing, but now gz r dv prime over r minus r prime. Right? Expressions that are analog to the case of finding a voltage for a charge distribution. Only now we take the xyz components of the current density as charge distribution. They're not actually charge distributions, but we take them as analogous charge distributions because we are solving Poisson equations, right? We can now combine all three components. So what happens if I combine all three components to find the A vector at any position in space R? Right? I just sum those up, right? Add x hat, y hat, z hat, and then I can take the integral out. Right? I can always take the integral out and then move the x hat in Cartesian coordinates. The x hat, y hat, z hat are always constant regardless of where we are integrating, right? So I can move them in and then I sum up the vector j. So I get this expression mu naught over 4 pi integration of the volume of j r prime dv prime over r minus r prime, Weber over meter. And this is A as found from Ampere's law. It is the same as the A that we found from the Boyer-Savart law. It is the same, but it's kind of concealed because we're integrating with respect to charge density. Sorry, current density rather than current filament. But let's do this. Let's assume that the volume is a very thin wire, right? Such that, right? So instead of the current being distributed everywhere in space, it's distributed in a very thin wire, such that we can take a small segment of that wire, and we end up with like this very small cylinder, right? And then dv prime here is going to just be dl. So this is dl prime dot, and this is ds prime. This is the cross-sectional area of the small cylinder, and dl is the length of the cylinder, right? ds prime. We just now this is dotting two vectors gives us a scalar, right? So we just express dv prime for a hypothetical thin wire. It still has a volume, and we can make the wire as thin as we want, but we can express dv prime as dl dot ds. Right, and we can plug that back in the expression for A. So A, R, R. You can still, by the way, use this equation. Right? I just want to show you that for the case of a thin wire filament, we get the same expression for A as we got from the Boyer-Savart law. when we start from Boyce-Haver law. And we need to show that consistency, right? So AR is going to equal mu naught over 4 pi integral over V prime J R times dl prime dot ds prime over r minus r prime magnitude. Okay, what we want to do now is we want to define this triple volume integral into a surface integral and a line integral. We want to integrate over dl, this is the line integral, and then integrate over ds. We're just separating a triple integral into a double integral, surface integral, and a line integral, right? And then while we're doing that, I need I want to kind of express this differently. So this is a dot. dl is always in the same direction of ds by definition, right? We defined it here as this small thin cylinder. So dl is always in the same direction as ds. So this is, I can look at this as dl magnitude times ds prime magnitude. That's what this is. And then I have the j vector. What I want to do now is I want to extract the directional, and the directionality of j, by the way, is the same as the direction of dl by definition. J is going this way. So I want to extract the information about direction from j and attach it to dl. If I do that, I get this expression. I get magnitude j times magnitude ds prime, right? And then I extracted the information about the direction from j and just attached it to dl. So I get dl prime as a vector. Those two expressions are equivalent, right? All I did in this expression is I took the direction information and attached it to dl so that I can get the dl prime vector. So direction, magnitude times direction gives me dl prime, and then all I took from j is just the magnitude, right? This is now equivalent to j dot ds. What I'm trying to say is that this expression is going to be equivalent to this, right? Of course, dl prime. Okay. So I can rewrite a r as a mu naught 4 pi. Now I want to separate the integrals. I want to take an integral over the length, line integral, and then I want to take a surface integral over the width here, right? Over the cross-sectional area of the small cylinder, right? So that will be j r prime. Remember r prime here. I put r prime, yeah. We said I can equivalently express this as ds prime, right, over r minus r prime dl prime. Okay, now I am integrating over this tiny surface, right? Let me do it in red. Right. Notice as I'm integrating over the surface, r minus r prime is not changing much, right? So r minus is this distance, right? R minus r prime is this distance. It doesn't change much when I'm integrating, because my small volume, I expressed it as an extended cylinder, right? So as I'm moving across dl, r minus r prime is going to change, but as I'm moving along the surface, r minus r prime does not change much. So I can remove this outside the surface integral, and I end up with just integrating j over dot ds. What happens when you integrate j over a cross-sectional area? You get I, right? The cross-sectional area, of course, is the wire, is the conductor. We are assuming that it's a very thin conductor, right? So because it's very thin, approaches zero, as we move across its cross-section, r doesn't vary much. We can take it out of the integral, and then I'm taking the surface integral of j over the cross-section of the thin wire. That gives me, this gives me the total current I. This is the logic. So I end up with the total current I can take it out, over 4 pi line integral of dl prime over r minus r prime magnitude. This is exactly the expression for A that we got starting from the Biot-Savart law for a current filament. So we have shown, let me see if I have this. We have shown that if I start from the Biot-Savart law for a current filament, I get an expression for A. If I start with Ampere's law in general, I get also an expression for A for a current density. If I as a general case, if I go back to the special case of a thin current filament, I get the exact expression for A that I get from the Biot-Savart law. Okay, so Biot-Savart law and Ampere's law are consistent with each other, and they give me the same A, which gives me the same B, because B is just the curl of A. Okay. The final thing I want to say about A is this. Remember the total flux going through a surface? Total flux, we said, is just the surface integral of B dot ds, right? We also can find the total flux in terms of A, right? And it's an application of Stokes' theorem because B is now curl A dot ds. I mean, this is the surface integral of a curl, right? So this is, so this, the total flux becomes just the contour integral, the path integral of A dl. So the flux going into a certain surface, crossing a certain surface, is kind of easier to find using A, because using A, the double integral, the surface integral, turns into a contour integral on the boundary of the surface. So on the boundary of the surface, just take A and take the path integral of A along the boundary of the surface. That gives you the total flux. Right? So this is the last thing I wanted to say about the magnetic vector potential, and with this we conclude. What chapter number is this? We conclude chapter 8. All right, thank you guys. And next we're going to start talking about some properties of the magnetic materials, similar discussion as what we did for dielectrics. We're going to discuss the equivalent phenomena to polarization for the magnetic field, which is exactly the same as polarization, only it has a different name. We call it magnetization. All right, thank you guys.